Okay, in previous courses, we are focusing on the mechanical properties, okay, such as UTS, ultimate tensile stress, and the yielding stress, Young's modulus, and so on. And also we introduce the imperfections, such as the point defect, including the vacancies, interstitial sites, and so on. And also the line defect, such as the dislocations and the area defect, like the grain boundaries, right? And also we introduce the fracture mechanics, the fracture toughness, that is the ability with the energy ability for crack propagation with initial crack inside a materials. Okay, and today's course we focus on the electrical property. Okay, electrical properties of a material. So the issues we have to address in this chapter is the what the issues we have to realize for the materials. I mean the electrical properties for materials. So how are electrical conductance and the resistance? And what are the physical phenomena that distinguish conductors, semiconductors, and insulators? And for metals, how is the conductivity affected by imperfections, temperature, and deformation? And for semiconductors, how is conductivity affected by impurities and doping and temperatures? Okay, so so you guys must learn some you must learn the Ohm's law from like electronics course, right? And what is Ohm's law? That is the voltage drop is proportional to the product of current and the resistance. Okay, so for example, we have the sample is a metal rod with the length L and the cross section A. Okay, and when we apply a voltage, we apply the voltage drop between two ends of this metal rod, and the current will flow through this metal rod, right? And the for example, we fix the voltage drop. We fix the voltage drop. If the resistance of this metal rod is higher, so what we get, what's the phenomena of the current flow? Right, we can fix the voltage, right, by a power supply. And if this material has the higher resistance, that means the current become small, right? Right, because it's because the voltage drop is proportional to the product of current and resistance. Okay, and there are two materials property: resistivity and conductivity. Resistivity and the conductivity and materials properties. Okay, so when we say its materials property, that means it's geometry independent. Okay, it's geometry independent. Okay, so resistivity is a materials property and is independent of sample. Okay, for example, so we have the Ohm's law, right? Ohm's law as the voltage drop equals to current times resistance, right? And if we have a sample, which is the metal rod, and we can normalize by its geometry. Okay, we can normalize by its geometry. Okay, therefore the voltage drop divided by the length of the metal rod and the current divided by the cross section. And there's a constant here called the resistivity, and its unit is ohms meter. Okay, and this constant is resistivity, a material's property. Okay, material's property. And the conductivity is the inverse of the resistivity. Okay, conductivity is the inverse of the resistivity. Okay, and resistance is geometric dependent. Okay, geometric dependent. Okay, therefore the resistance is that we can measure it by using a multimeter. Okay, we just can use the multimeter to measure the resistance. Okay, and its geometry has to be fixed. For example, we have a metal rod with a cross section, fixed cross section and length. Okay, therefore the resistance can be measured and it's geometric dependent. Okay, therefore it's a geometric dependence, so we can write it as the resistivity times its geometric vector. Okay, geometric vector. Okay, and this can be measured. Measurable. Okay. And resistivity is a microstructure sensitive properties. Of course, if there are some imperfection or doping, that will highly affected. Okay, highly affected. Okay, and conduction occurs when charge carriers move as a result of diffusion, drift, and combination of diffusion and drift. Of course, diffusion we already discussed in previous chapters that is highly correlated to temperature and concentration gradient, right? And drift is due to the applied electrical and magnetic field. Okay, and the charge carrier here we mentioned is electron. Okay, or hole. Okay. Of course, we're going to focus on electron first. Okay, so the drift velocity, when the electron moves inside a material, and the average velocity of the electron moving inside a material is called the drift velocity, and this drift velocity is highly correlated to the imperfection. The imperfection can be regarded as the barriers. Okay, the barriers inside a material. If we have numerous impurities inside materials, that means the electron movement retarded by those barriers, right? And the drift velocity reduced. Okay. Okay, and for the metal, the charge carriers is electron. Okay, we already know that for the metal bond, the free electron cloud, right, is dominated by its conductivity or electrical properties are dominated by the free electron cloud. Right, therefore the charge carriers in metal is electron. Okay. Okay, it's electron. However, for semiconductors, covalent bonds dominate. Okay, therefore the charge carriers could be free electrons or holes. Okay, free electron or holes. Okay, it depends on either p type or n type. Okay, p type or n type. Okay, if we have time, we're gonna introduce the N-type and P-type semiconductor later. And for the ionic bond, the ionics diffusions by the vacancies. Okay, by vacancies, and it has to be maintain the charge neutrality. Okay, the charge neutrality has to be maintained. And okay, so which will conduct more electricity? For example, we have two metal rods. Okay, two metal rods. For example, we have two metal rods, 1 and 2. And what's the difference between these two metal rods? Diameters and lengths. That's mean the geometries, right? The geometries are different. The geometries are different between these two metal rods. Right? So we can think of the water flow in a pipe. Which one has the higher resistance to water flow? That means the water flow through the simple 1 and flow through the simple 2. Which was easier? Which was easier? Of course, the simple 2, right? Because the simple 2 has the what? Larger diameters and shorter lengths, right? And shorter lengths. Okay. So the resistance is geometric dependence. Okay, resistance is geometric dependence. Okay. Therefore, we can say, for example, we can say the resistance equals to what? Resistivity times the length divided by the area, cross-section. Right, cross-section. Therefore, if we have a larger cross-section area, this is higher. A shorter length, L, distance is L. So we get the lower resistance, right? We get lower resistance. Okay. So what is the minimum diameters of a wire so that the voltage drops more than 1.5 volt? Just provide you an example. You have a copper wire. We have a copper wire with 100 meters, and the current equals to 2.5 amp. Okay, and the voltage drop has to be less than 1.5 volts. Right? And then we know the resistance equals to the length divided by cross-section and conductivity, right? The inverse of resistivity, right? And equals to the voltage drop divided by the current by Ohm's law, right? Right? This is Ohm's law. Ohm's law, right? And therefore, we can figure out the diameters from the cross-section area, right? And you can check the materials property of the copper. I mean, the conductivity of copper, because it's a electrical property or materials property. Okay, materials property. And finally, we can get the diameter of this copper wire is 1.87 millimeter. Okay, if we desire its voltage drop as smaller than 1.5 volt. Okay. So further definitions. We already know the Ohm's law, right? Ohm's law is the voltage equals to I, the current times resistance. Always say the voltage drop. Okay, and further definition or another expression of Ohm's law is J equals to sigma times E. And what is J? J is the current density. Okay, current density equals to the current divided by the cross-section area. Okay, cross-section area. And E equals to the electric field potential. Okay, so if you guys already learned the some electronics course, you will know the electrical field potential equals to voltage divided by the distance. Okay, voltage divided by distance, or the voltage drop divided by the length difference. Okay, okay. Therefore, we can plug this two. And plug this inside here, right? And we get the electron flux equals to the conductivity times the voltage gradient. Okay, voltage gradient is the electric field potential. Okay, and equals to the number of charge carriers times the charge, number of charge, and times the drift velocity. Okay, drift velocity. And the current carriers, or we say the charge carriers, are electron in most of solids, especially in metal. Okay, of course, ions can also be as the charge carriers. Okay, and the conductivity, which is the inverse of the resistivity of a materials, can be written as equations, as following equations. Okay, so this is a conductivity, right? Equals to the number of charge carriers, and Q is the charge on each carrier. Okay, charge on each carrier. And the unit of charge is coulomb. Okay, C. And the mu is the mobility of charge carriers. Okay, mobility of charge carriers. Okay, for electron, for each charge carriers has 1.6 times 10 to minus 9, sorry, 1.5 times 10 to minus 19 coulomb. Okay, this is for metal. Okay, this one's for metal. For a semiconductor, we have to divide it by two mobilities. Okay, two mobilities including the negative charge or positive charge. Okay, so it depends on this semiconductor is N doping or P doping. Okay, therefore we have to divide it by two conductivity. And the N here is the same as the number of charge carriers with electrons, and the P is the number of charge carriers of holes. Okay, and the mu N is the mobility of electron, and the mu P is the mobility of holes. Okay, therefore the conductivity of a materials might be increased by increasing number of charge carriers. Okay, it's very important in semiconductor, and also increasing the drift velocity. Okay, it is important in metals. Okay, so you have to think of, okay, if we want to increase the mobility of semiconductor, what's the process we should work on? Okay, if we want to increase the mobility, the mobility of charge carrier in metal, and what is the process we should work on? Okay. Okay, so let's see the comparisons of conductivities at the room temperature. Okay, so for metals, for metals, silver, copper, and iron, its conductivity is about 10 to 7. Okay. However, for semiconductors, whose conductivity has a wide range, depends on what kind of materials. Okay, for silicon, its conductivity is about 4 times 10 to minus 4. Okay, for gallium arsenide, it's about minus 10 to minus 6. Okay, for germanium, whose conductivity is about 2, right? I mean, it totally depends on the what kind of semiconductors. Okay, and for ceramics, whose conductivity should be extremely high, right? Because it's based on ionic bonds or the mixed bond of ionic and covalent. Okay, covalent. Even for the soda lime glass, okay, its conductivity is about 10 to minus 10 to 10 to minus 11. For concrete, its conductivity is about 10 to minus 9. Okay, for aluminum oxide, its conductivity is about 10 to minus 13. Okay, and for polymers, of course, for polymers, while its conductivity is similar to ceramics, or even higher, Therefore, these two, ceramics and polymer, usually they are insulators. Okay, they are insulators. Okay. Okay. In order for charge carriers to conduct, they must be able to increase in energy. Energy of carriers can only increase if there are available energy states to which they can be promoted depending on the type of materials involved. And there may or may not be a sizable energy gap between lower and higher energy states. And the energy gap is called the band gap. Okay, let's look at the figure to define what is band gap. Okay, and what is band gap? Okay, as number of bonds atoms increase, the energy level of valence electrons split. And only two electrons available for each energy state. So do you still remember the first few classes? We mentioned the quantum numbers. The quantum number, we have the KLMN orbitals, and we have the suborbitals, right? S, P, D, F. So do you guys still remember that? So what's the electron in s orbital? How many electrons should be in s orbital? 2, right? 2. So how many electrons should be in p orbitals? 6, right? And D, 10, right? So do you still remember that? Okay, and what's the energy state of d orbitals? 5, right? And energy state of p orbitals? 3, right? So if you already forget it, just check the I think the second courses. Okay, I already introduced you these the concept of energy state. Okay, and the Pauli expulsion principle mentions that the only two electrons is available for each energy state. No more than 2 electrons. No more than 2 electrons can be exist in each energy state. Okay. Therefore, the valence electron are split. when the number of bond atoms increase, okay, because they are going to be getting closer and closer. Okay, for example, we have one atoms and the level of electron, and this is the level of electron, and this is the energy of electron energy. And if we have two atoms, right? As we mentioned that you need only 2 electrons, right, for each energy state. Okay, if we have 2 electron. Okay, and the electron energy will split. And we have a small number of atoms. Okay, and we have a higher number of electron. And this energy, electron energy, will further split. And finally, there are gap formed between 2 energy of electrons. And this gap called a band gap. Okay, so let's look at this figure. It shows the interatomic separation versus the energy, electron energy. Okay, electron energy. For example, if we have 2 atoms, right? 2 atoms, and it has the 1s orbital. Okay, 1s orbital. And when these 2 atoms come to closer, okay, come to closer and closer, and these orbitals will overlap it. Okay, will overlap it. When these orbitals overlap it, that means maybe the electron in each energy state will, the number of electron in each energy state will more than 2 electron. Okay, that means these atoms squeezing together and this orbital overlap it. For example, we have the structure, metal structure is FCC or cubic structure, right? For example, like this. Okay, and we have a lot this periodic fashion, right? Like this, extended this structure, right? And each atom has its s orbital or 2s orbital or the the 3p or 4d orbitals, right? And when those number of atoms come together, and these orbitals will overlap it, right? Will overlap it. Okay, we'll overlap it. When higher number of atoms is the overlapping the orbitals, and this Pauli principle, the Pauli explosion principle, might violated, right? Might violated. Therefore, the electron energy state will split. Okay, so for example, I have 2 atoms with the orbitals, right? This is the atom and atom of the, right? And with this orbital overlap it, and the Pauli explosion principle will be violated. Therefore, the valence electron split. Okay, split. Okay. Okay. Therefore, for this this electron number increase, that means the interatomic separation decreased, right? And the electron state, electron energy will split. Okay, we are split. Okay, you know what I'm saying? And for the longer distance between atoms, well, for example, at this position, we still have the 1s electron state, right? 1s electron state, 1s electron state, and 2s electron state, and so on. And when these atoms come closer and the number of atoms increase, right? That means the interatomic separation decrease, right? Decrease. And the energy state split, or the valence split. Okay, valence split. Okay, therefore we can see, so for the valence band, that's mean the field, that's mean electron field, the highest occupied energy level. And what's that mean? What's that mean? We already mentioned that for the longer distance between atoms, it's still one state, right? And when the number of atoms increased and they come closer and closer, and the energy level split, okay, split. And so you must remember that we have the distance called the equilibrium interatomic spacing, right? R naught, right here, right, at this distance. Okay, and this is the split energy. Okay, and we can see there's the valence band. Valence band is the electron full field, right? It's the highest occupied energy level, right? And at this range here. Okay, and the higher energy state occupy the energy level is the valence band. Okay, therefore in this region it's electron field. So you can think of this electron full field inside this region. Okay, this region. And for the conduction band, in the conduction band, basically it's empty. That means no electron field. No electron field. For example, maybe this is 1s, this is 2s. Let's give some example. Okay, therefore, we know that for the 1s orbital at the equilibrium interatomic spacing, we know this valence band, or we know this electron full field at a specific interatomic spacing, right? However, at this distance, at this spacing, it's 2s energy state is empty. It's empty. Okay. Therefore, you have a gap between these two energy level at equilibrium interatomic spacing. Okay. So for two orbital without any electron at equilibrium interatomic spacing. Okay. And 1s orbital is full filled with electron at equilibrium interatomic spacing. Okay, therefore we can define the conduction band. It's here. This range. And this range is called the valence band. Okay, valence band. Okay. Therefore, for example, the band structure of a sodium and other alkali metals in column 1A of periodic table only has one valence electron, right? One valence electron, and the outmost 3s orbital is only half filled. and electrons occupy the lowest energy level. And when electrons gain energy, they are excited to the higher energy level. Okay, and for example, for the sodium, right, only has one electron, right? And outermost orbital is 3s with one electron, right? We already know that the two electron can be filled in s orbital. Okay, therefore you only half of an electron field, in 3s orbital. Okay, at equilibrium spacing. Okay, so this point is equilibrium spacing. Okay, it's equilibrium spacing. Okay. Okay, therefore this is called the valence band. Okay, valence band. And when the electron gain energy, they're excited to jump to the high energy level. Therefore, the electron will jump from the valence band to conduction band, right? Jump to a higher energy level. Okay, jump to the higher energy level. Okay, because the 3sp is this higher orbital, right? Without any electron field. Without any electron field. Okay. Okay, the band structure of semiconductor and insulator. Okay, the elements in group 4 has a valence of 4, but they are not very good conductors due to strong covalent bonds, right? And a large band gap separates the valence and conduction bands, leading to poor conductivity. Okay, for example, this is the band structure of carbon. Well, carbon is basically its conductivity is higher than that of other semiconductors. Okay, so you can see this is the valence band. It's the valence band. Okay, valence band, and it's a conduction band. Why? It's empty electron. Okay, and the valence band is filled with electron, and there's a band gap between these two bands. Okay. Therefore, we can summarize the band structure of solids for metals. The valence band, and the conduction band are overlapping. Okay, are overlapping. That means the electron can jump between these two bands freely. So that means the electron can come back and forth freely. Okay, because these two bands are overlapping. However, for semiconductors, there is a band gap between these two bands, conduction and the valence band. And this band gap, well, is not large enough. Well, it has a gap, but not large. Okay, you know what I'm saying? There's a gap between these two bands. However, if we push the electron, push a little bit, this electron, you will be excited to jump to the conduction band. Okay, and for the insulator, that means the gap, the band gap is huge. Well, the electron is not easy to be excited. Okay, for semiconductor, electron might be jump to the conduction band by exciting the by promoted by some energy, external energy, such as the thermal energy or potential energy, and so on. Okay. However, for the insulator, the electron, if the electron want to jump to the conduction band, we need much higher energy to promote it or to excite it, to excite the electron jumping to the conduction band. Okay, you know what I'm saying? So, like in metals like copper or silver and so on, they have a very good conductivity, right? You even can measure this resistance by the multimeter, Okay, for the semiconductors such as silicon, what else? Germanium, carbon, and so on. Okay, so what is insulator? What is insulator? Like ceramics, right? And the polymers, plastics, and polymers. Okay. So I already mentioned that for the metals, they're good conductors, right? And thermal energy put many electrons into a higher energy state. Okay, so the thermal energy is the external energy to excite the electron, right? To excite the electron. Okay, so this is the metal. Okay, metals, and these empty band, that's the conduction band and the valence band overlap it, right? Therefore, they can move. This is the field electron, right? And this electron can jump to here and return, jump to here and return, jump to here. No, it can move freely, okay, inside metal. Okay. And for the semiconductor, there's a gap between. Okay, there's a gap between the field valence band and the empty band. Okay, therefore the electron want to jump to the empty band. Well, we need to push it. We need to push, okay, by external energy. Okay, by external energy. Well, it's different from the metals. Okay, it's different from the metals. Okay, for metals, the electron can jump to the empty band, to the conduction band freely, without any external energy. Okay, if there's external energy like thermal energy applied, that's mean the higher number of electron can jump to the valence band, jump to the conduction band. Okay. However, for semiconductor, we need a higher energy. We need higher external energy to push electrons, to excite the electrons to jump to higher energy level to the conduction band. Okay, to the conduction band. Okay, and for the insulators, we need extremely high energy. Okay, we need extremely high energy to excite it, to push electron to jump to the higher energy level. Okay, and mostly this electron, if this external energy is not high enough, this electron cannot jump to the conduction band. Okay, you are returned. Okay. So the charge carriers dominate the conductivity of materials. Okay, of materials. And I already mentioned that there are two types of charge carriers. One is called the electron and hole. Right? Two charge carriers. Okay, two charge carriers. Okay, and the drift velocity dominates its conductivity, right? The drift velocity of those charge carriers dominates its conductivity. Okay, therefore we can see this figure. It shows clearly the valence band, which is full filled or partially filled, the partially or fully filled with electron, and the conduction band is empty without any electron. And there's a distance between these two bands is called the band gap. It's called the band gap. Okay, if we wanted this charge carriers jump to from the valence band to the conduction band, we need external excitation. Okay, we need some excitation such as thermal energy or the optical energy or the electrical energy to push electron jump from the valence band to conduction band. Okay, therefore the higher temperature promotes more electrons into the conduction band, and electrons scatters by impurities and grain boundaries. Okay, and we can define we can change the conductivities of metals by increase the mobility of charge carriers by increase the mean free path of electron. Okay, mean free path. Lambda E equals to tau times drift velocity. Okay, and what is mean free path? Mean free path, lambda E of a gas molecule is its average path length between collision. Okay, okay. In the electronic materials, it is charge carriers, the mean free path, lambda E of charge carriers. Okay, the mean free path, lambda E of charge carriers is its average path length between collision. Okay, and what is the temperature effect? How important is of temperature for its electronic property? Okay, with increasing temperatures, atoms in a metal evaporate more and scatter more electrons, and this decreases the mean free path of electrons and increases the resistivity. And change in resistivity can be written as the function of the temperature. Okay, it's an experimental function. Okay, it's an experimental function. Okay, here. Okay, so it's a resistivity by temperature, and it's a resistivity in room temperature. Okay, and it's a constant. I will introduce this constant later. Okay, therefore, this equation dominates the resistivity as a function of temperature. As a function of temperature for metals. Okay, for metals. Okay, so we can work on the experiment. We can work on the experiment of the resistance with temperature in metals. Okay. Okay, and this is a temperature. It's a temperature, and this is resistance, right? And we can apply the different temperatures to a metal. For example, for a metal rod. Okay, we can put a metal rod in the oven, put it into an elevated temperature, and measure its resistance, right? So we can measure its resistance at T1, temperature 1, and we get a resistance, right? Resistance 1, R1. and we can measure its resistance at temperature 2. Right? Therefore, we can work on a different point here, here, and here. Right? We can measure resistance corresponding to different temperatures, and we got a linear relation. Okay, we got a linear relation of resistance corresponding to different temperatures. Right? And we can draw this linear relations to find out the intercept, with x-axis. Okay, so we get a triangle here, right? And therefore we can find out a relation, right, from this triangle. Okay, from this triangle. What this relation is? I think you guys already learned this from your elementary school or junior high, right? Or junior high. So we can find a relation is this. R2 divided by R1 equals to T plus T2 over T plus T1. And what does the capital T means? The capital means the intercept. The intercept. Okay, the intercept of this linear relation. Okay, for this example is right here. Okay, T here. It's the intercept. Okay, it's a materials property. Why? Because we can do the experiment to find our linear relation between resistance and temperature, right? And then we figure out this intercept, right, with x-axis. Therefore, it's a temperature. It's a temperature. Okay. So at this point, it's zero resistance. Zero resistance. That means it's a superconductor. It's a superconductor. So if you guys have read some technological news that some scientists developed a semiconductor at high temperature. High temperature. Usually the high temperature means maybe minus 100 Celsius, for example. Wow, it's a high temperature. Okay, and theoretically, the superconductor phenomena occurs at the absolute temperature, minus 283 Celsius, theoretically. Okay. Okay. Well, it's not the topic we should cover in this course, but just that you guys to realize it a little bit. Okay. Okay. Therefore, we can estimate the different working temperature. We can estimate the material's resistance at different working temperature. Okay. Okay. Therefore, we can calculate this relation, right, from that triangle. From that triangle to get the resistance at a specific temperature, RT. Okay. This RT can be T2, T3, T4 at different temperature, and T1 mostly it's room temperature. Okay, it's room temperature. Okay. Okay, and the 20 means 20 Celsius. Okay, it's 20 means 20 Celsius. Okay, 20 Celsius. Okay. Therefore, okay, we arrange this relation from here to here. Right? Okay. and we can rearrange it as the from the numerators with the t plus 20 plus t minus 20. Okay, because this can be deleted. Okay, so these two equations are the same. Okay, are the same. We just use some operations to get the coefficient. It's called the temperature coefficient of a resistance. Okay. 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 Therefore, we can, and then we can rearrange this equation, right? Right. Okay, and this term can be 1 here. Gamma sign. And this term can be rearranged in this term. Okay. Okay. And therefore we define the constant. We define the constant alpha is this term. Okay. I just erase that off then and it will be clearly. And we define the alpha 20 equals to this term. Okay, and what's the definition of alpha 20? It's the temperature coefficient of resistance as 20 Celsius. Okay, and the physical definition of this coefficient is that the temperature reaches 1 Celsius, the ratio between the resistance increase and the original, the temperature reaches 1 Celsius, now the ratio between the resistance increase and the original resistance. Okay, therefore we can get this. Okay, I just derived an equation. I just want to express the calculation how to get this resistance as a function of temperature. And this equation is from experimental work, from this experimental work to get this equation. Okay, to get this equation. Okay, so we can compare with the resistivity and the temperature coefficient of a resistance. Okay, we already figure out the temperature coefficient of resistance, right? And we just have a comparison between different type of materials. Okay. Okay, and it's a metals. It's metal. Metals always with the positive temperature coefficient of resistance. Okay, so what the definition is positive temperature coefficient. Okay, they are all positive. Okay, they are all positive. They're all positive. And most of the semiconductor and the ceramics whose temperature coefficient of resistance are negative, mostly are negative, right here, mostly are negative. Okay, so how to explain this? I mean, how to explain the physical meaning of this positive and negative coefficient, temperature coefficient. How? So the negative temperature coefficient means that what? When the temperature increase, its resistance decrease, right? When the temperature increase and its resistance decrease. For the positive temperature coefficient means that when the temperature increase, its resistance increase. Okay, and why? So from this table, you can realize that in metals, if we apply a higher elevated temperature, its resistance increase, right? Why? Because the temperature, the thermal energy facilitates the electron movement, and this thermal energy increase the possibility of electron collisions. Okay, and this collisions increases this kind of a barrier, this barrier of electron movement. Okay, however, for semiconductor, as we mentioned previously, that we need external energy to promote electron jump to conduction band, right? Therefore, we apply the elevated temperature, it will become more conductive. That means its resistance decrease. Okay. Okay, so today's course will ended here, and next course I will talk about the impurities. Okay, the conductivity and the electrical properties with impurities.